You know that physics of low temperature, which is studied in thermodynamics, is a very important branch of physics. Actually, in several processes we need a very low temperature. So actually in thermodynamics we study the physics of low temperature. And there are several methods to obtain a very low temperature. Now, as our present concern is about the magnetism of substances, and previously we have learnt in very detail the classical and quantum theory of diamagnetism and paramagnetism. Actually, in fact, related to the paramagnetic substance, there is a very important phenomenon which is actually called paramagnetic cooling. In fact, in paramagnetic cooling, you will see that we will use a paramagnetic salt and achieve a very low temperature of the order of 10 to the power minus 3 Kelvin. But this much a small temperature is obtained by a particular process, and that is actually a process of adiabatic demagnetization. So, in present lecture, you will see the discussion on paramagnetic cooling, or you can say that adiabatic demagnetization. Okay. In fact, before this experiment, a temperature of 0.3 Kelvin have been obtained by a particular process in which the liquid helium was evaporated under the reduced pressure condition. And in this process, people get a temperature of the order of 0.3 Kelvin. Okay? But if your aim is to obtain even more a smaller temperature, that is a temperature which is much smaller than this 0.3 Kelvin, okay? Then to produce the still lower temperature, two scientists, P.Debye and W.F. Giaugue, has suggested independently a method which is called adiabatic demagnetization. And by this process you will see a temperature up to 10 to the power minus 3 Kelvin of this order can be achieved. Okay? In fact, at present, this method is universally accepted method for producing low temperatures. Okay? And as I have told you that by this method, a temperature of 1.0 into 10 to the power minus 3 Kelvin or even less than this has been obtained. Okay? So in this lecture, we are going to see what is this phenomenon paramagnetic cooling or adiabatic demagnetization and how we can obtain the temperature of this order 10 to the power minus 3 Kelvin by this process. Okay? In fact, when you talk about the paramagnetic cooling or adiabatic demagnetization, actually this method is based on a very fundamental fact of thermodynamics. You know, you have definitely studied in thermodynamics that at fixed temperature, the entropy of a system having magnetic moments, for example, paramagnetic salt, is lowered if magnetic field is applied. When you will apply the magnetic field, then it is found that the entropy of the system which has actually the paramagnetic moment, permanent paramagnetic moment, the entropy of such a system is actually decreased, okay, if you place the substance in a magnetic field. What's the reason? You can easily understand why the entropy of such a substance whose molecules or atoms has permanent dipole moment, when placed in an external magnetic field, its entropy decreases. Because you know that entropy is actually the measure of disorderness. Okay? And in a paramagnetic salt, which has actually the ions with permanent dipole moment, but those ionic dipoles or atomic dipoles are randomly distributed. They are in a state of they are actually in the most disordered state. So entropy is high. But when you apply the external magnetic field, you know, each ionic or atomic dipole experience torque due to the magnetic field, and the atomic or the ionic dipoles get aligned along the line of applied magnetic field. And so a system which was actually in a state of most disorderness, now it is in an ordered state. And you know, entropy is the measure of disorderness. So since due to the magnetic field, disorderness decreases, our system becomes ordered, that's why its entropy decreases. This is a basic fact of thermodynamics. And actually, this idea is utilized in paramagnetic cooling, or you can say the adiabatic demagnetization. Okay? And now, for understanding this process, let us see this figure. Actually, in this figure, you can see I have plotted a graph of entropy of such a material like a paramagnetic salt or the salt of iron group in against of temperature. Okay, you can see. So this is a plot of entropy versus temperature. Okay. Now you can see when a magnetic field is zero. See here, H when H is zero. Okay. In the absence of magnetic field, that means H equal to 0, you can see the curve OCA, here is O, this curve OCA, see here, OCA, okay, and when H is not equal to 0 but H is equal to H, then the graphical plot of entropy in against of temperature is this curve dB, or you can say BD. So OCA is the curve obtained by plotting entropy in against of temperature when we have applied no magnetic field. Okay? But this dB is the curve obtained after plotting entropy in against of temperature when a magnetic field H has been applied. Okay? Now you can see this curve dB lies below the curve OCA. You can see. And as the curve dB is below the curve OCA, so you can say that the entropy of the system is lowered by the application of magnetic field. So when magnetic field is applied, the entropy decreases. And why entropy decreases? I have already stated you. Because you know, this is due to the fact that disorder in the system decreases as most of the magnetic dipoles align along the field direction, and the entropy decreases as the disorder decreases. Okay? So in presence of magnetic field, the curve dB obtained after the plot of entropy versus temperature is below the curve OCA, which has been obtained when there was no magnetic field applied. Okay? Now let us see. We consider that at a fixed temperature Ti, see here, at a fixed temperature Ti, If we proceed along the curve AB, see in this figure, if you proceed along this curve AB at a fixed temperature Ti, okay, then it would mean an isothermal change because temperature is constant. And when you say that our system is suffering an isothermal change in moving from the state A to B, it means you have kept the system in contact of the surrounding at constant temperature. Okay. Now you can see if the system changes its state from A to B, in state A you can see that the value of the magnetic field is 0, and in state B the value of magnetic field is not 0, it is equal to H. Okay. So on moving from A to B at a fixed temperature Ti, the field becomes H from its 0 value. Okay. And thus entropy will fall along AB. Okay. So you can see that corresponding to point A, the value of entropy is this much. You can see the figure. This is the value of entropy, let us say SA. But corresponding to this B, the value of entropy is SB. And you can see from this figure that this SB is less than SA. So after the application of magnetic field, entropy decreases. Now if field is switched off, it means you make H equal to 0. Okay? And the system is isolated from the surrounding. It means now the system is not kept at a constant temperature. Okay? Then the state of affair will be represented by an adiabatic process represented by this curve BC. You can see. Because you know, in case of adiabatic process, our system is isolated. It has no connection with the surrounding. There is no exchange of heat energy between the system and the surrounding. So, after this state B, the system changes its state to C via the process BC, which is an adiabatic process. Okay? And you can see, in state B, magnetic field was H, not 0. But when it reaches to the state C, the magnetic field becomes 0. You can see here. This OCA, for the curve OCA, H is equal to 0. So this is just a process of this is an adiabatic process, and you can say this is adiabatic demagnetization. Why demagnetization? Because after application of magnetic field, the material gets magnetized, and when you remove the field, the material gets demagnetized. So here, field becomes 0 after its non-zero value. So this BC is just a process of adiabatic demagnetization. Okay. Now, you can see the magnetic field reduced to the magnetic field is removed without changing the entropy of the system, because you know that in an adiabatic process there is no change in entropy. You have definitely studied in your course on thermodynamics that ds is equal to del q over t, you know, and in an adiabatic process this del q is equal to 0, and so ds is equal to 0. So there is no change in entropy during the adiabatic process. So when the system follows the process BC, which is an adiabatic process, in this process entropy of the system will remain constant. And it is evident from this curve that when the system is in a state B, okay, when its temperature is Ti, field is H, okay, then entropy is equal to SB. But when the system is in a state C, when its temperature becomes TF and field becomes 0, then again you can see that entropy remains same, that is equal to SB. That does not change. Okay. So entropy remains same. So actually, as a result, the temperature is reduced to TF. You can see, initially when the system was in state B, temperature was Ti, but when it reaches to the state C, its temperature becomes TF. And it is evident from this figure that this TF is less than Ti. So this is actually called a cooling process, paramagnetic cooling, because the system which is taken in this case is actually a paramagnetic salt, and all these thermodynamic operations have been performed on that paramagnetic substance. So this is called just a paramagnetic cooling. Okay. So if this process is repeated, okay, then we can decrease the temperature of the system to a very lower extent. So you can say that the repeated cycle of this nature will reduce the temperature of the system very much. Okay? Actually, the process is called cooling by adiabatic demagnetization, as I have told you, and the system which has been taken in this experiment, actually that system must be pre-cooled to a temperature up to 1 Kelvin. It means when the system is taken for these operations, you must have the temperature of the system of the order of 1 Kelvin. And this 1 Kelvin temperature is achieved actually by other processes. And then this process is started. Okay. So I think you have understand what have been actually explained in this graphical plot of entropy in against of temperature. Actually, two scientists, Corti and Simon, developed an approximate formula for estimating the final temperature reached by this process of adiabatic demagnetization. And actually, the formula obtained by Corti and Simon is based on two assumptions. So you can see. Actually, what I have explained, I have actually mentioned all those things here, and you can note down these things in your notebook, and that will be a very good notes for your examination purpose. Okay. Now let us see. Actually, as I have told you, that two scientists, Corti and Simon, has actually developed an approximate formula, not a very accurate formula, for estimating the final temperature reached by this process of adiabatic demagnetization. Okay, and for this they made actually two assumptions. The first assumption says, in the absence of field H, the normal 2J plus 1 positions of the ions are separated by equal energy increments G mu B H. What you have understand? Actually, you know, if J is the total quantum number, then you know an energy level is splitted actually into 2J plus 1 energy levels in presence of magnetic field. And if these are the different energy levels whose number is actually 2J plus 1. If this is 1, this is 2, then finally this is 2J plus 1 level. And the energy separation, if you note the value of energy in this direction, between the two successive energy level is given by this formula. This is G mu B times H. Here you know G is the Lenz's splitting factor, mu B is Bohr magneton, and H is the applied magnetic field. Okay. And actually the magnetic moment and the entropy, these two are actually governed by Boltzmann distribution law. Okay. And since the entropy depends on the energy of the system and the energy difference between the two successive levels is actually equal to G mu B H. So according to the first assumption of Simon and Curti, the entropy of the system is a function of this factor G mu B H over Kb times Ti, where Kb is Boltzmann constant and Ti is actually the initial temperature. This is initial temperature. Okay? And this initial temperature of the substance is taken much greater than theta naught, where as I have told you that the system requires pre-cooling down to a temperature of 1 Kelvin. So actually this theta naught is the pre-cooled temperature, and this theta naught is of the order of 1 Kelvin. Okay? But Ti is much greater than this theta naught. Okay? Now, the second assumption is when field is removed, they assume that the energy levels are separated by Kb times theta naught. When field will be removed, H will become 0. And then what will be the separation between two successive energy levels? According to Simon and Curti assumption, that is proportional to Kb times theta naught instead of this G mu B H, because H is now 0. Okay? And therefore, you can say that now the entropy will be a function of Kb times theta naught divided by Kb times Tf. Okay? Kb times Tf, where Tf is the final temperature reached on account of adiabatic process, as you have seen in the graph. But you know that entropy does not change in an adiabatic process. So definitely this factor which of which the entropy is a function at initial temperature Ti, and this factor of which the entropy is a function of final temperature Tf. Since entropy does not change in an adiabatic process, and here our system transits from its initial state to its final state via adiabatic process. So definitely these two factors must be equal. Okay? That's why you can see I have written that as the entropy is constant during adiabatic demagnetization, so we can take this factor equal to this factor. Okay? So G mu B H over Kb Ti is equal to Kb theta naught over Kb Tf. Okay? Now this Kb and this Kb will cancel out, you can see, and you can get this Tf is equal to Kb theta naught over G mu B H times Tf. Okay? So in this way you can obtain the final temperature of the paramagnetic salt if you know its initial temperature using this formula. Actually this is not a very accurate formula, but this is an approximate formula developed by Curti and Simon. Okay? For example, if you consider that G is equal to 2 for salts of iron group, this is fixed. Okay? And let us take H is in kilo oersted, okay, and theta naught in Kelvin. Okay? In fact, in that condition, when you will put the standard value of Boltzmann constant Kb, this G equal to 2, mu B, which is Bohr magneton, it is also a universal constant, then Tf is equal to this much. This is 7.5 times theta naught over H times Ti. Okay? And so from this result it is obvious that this final temperature is proportional to theta naught. That is, it depends on the pre-cooled temperature. So if your aim is to get lower and lower temperature, the pre-cooled temperature should be also very small. Okay? And by using this formula, theoretically we can obtain the final temperature of the paramagnetic salt after this adiabatic cooling. Okay. In fact, for effective cooling by this process, the system, that is the paramagnetic salt, is to be pre-cooled so that theta naught is lower than 1K. As I have told you earlier, the value of theta naught is kept 1 Kelvin or less than 1 Kelvin. Okay. For example, if you talk about iron ammonium alum, this theta naught is kept at 0.061 Kelvin. Okay. And then if initial temperature is 1.2 Kelvin and H is 14 kilo oersted, then when you will substitute all these values in this equation 2, you will get that Ti will be equal to, not Ti but Tf. Tf will be equal to 7.5 times 0.61 times 1.2 over 14. And after simplification, you will get this much. So you can see by this rough approximation, we can have an idea of the final temperature obtained in cooling process. So you can see that this final temperature is of the order of 10 to the power minus 3 Kelvin. This is the order because this temperature will be equal to 3.9. This will be, not 3.9, but this will be 39 times 10 to the power minus 3 Kelvin. Okay. So order is this much. So I think you have clearly understand what is this process of adiabatic demagnetization or the paramagnetic cooling, and how the very small temperature of the order of 10 to the power minus 3 Kelvin can be achieved by this method. Okay. Thank you very much.